All right. Hello, everybody. Happy Monday or Tuesday, whenever it is that you see this. We are going to talk today about some other energy sources. Some of them we've kind of mentioned, you've seen in a little bit here and there, but some other energy sources that have been proposed that, at least as they are right now, they don't really work. Maybe in the future they might, maybe not. Don't really know. We'll find out. All right. And by the way, we're talking mainly here about energy sources for cars. Which cars present a unique challenge because obviously the car has to constantly be moving around. It can't just sit in one place while you bring the energy to it, like at a power plant. So here's an idea. Take a cat. Cats always land on their feet when they fall. Bread always seems to land butter side down when you drop it. So attach some buttered bread to the back of a cat. Obviously, then the cat bread will never fall. It'll just keep rotating, attach it to a generator, get infinite energy. Definitely going to work. Maybe not so much. All right. What about ethanol? We use ethanol a lot in our cars. I mean, a lot of gas stations have a pump that looks like this with all these different options for adding ethanol. But is that actually a long-term solution? Well, we get ethanol from fermenting yeast. Okay. Or fermenting corn, with yeast, mixed with water and kind of dissolve it, soak it in the water, add the yeast does its stuff, and when you're done, you get about 10% ethanol, 90% water. So you got to boil that, you have to distill it to boil the water, or boil the alcohol off to concentrate it. You end up with about 95% pure. We add then poisonous substances to it, so that then it couldn't be consumed, because that would not be good. If we could buy pure alcohol for like $2 a gallon, wouldn't be good for society. So we add poisonous substances to it, and then it can be used as fuel for cars. Now around here, most gasoline is at least 10% ethanol. Even just regular gas. If you look closely at regular unleaded 87, they will have somewhere on there that it contains up to 10% ethanol, and it usually does contain 10% ethanol. And then more modern cars oftentimes can run on fuel that's up to 85% ethanol. Okay. Now, when we burn it, it does produce carbon dioxide. Of course, we're burning it, makes carbon dioxide. But when then the next year we plant more corn, the corn that we grow will take that carbon dioxide back out, use it to make more corn that then we use to make ethanol, that then we burn to make carbon dioxide, that then gets used to make more corn. And so, in theory at least, by using ethanol, theoretically, we shouldn't be adding carbon dioxide to the atmosphere, as long as we're not using fossil fuels at all. Now, so that means that we'd have to be using ethanol or biodiesel or something to power our farm equipment, for example. But as long as we're not using any fossil fuels, theoretically, we shouldn't be adding carbon dioxide to the atmosphere. But it doesn't actually work as well as it's been promised. First of all, we're using land that we could be using to grow food to produce fuel. And I mean, as human population keeps getting higher and higher and higher, we need more and more and more food. We're already seeing food shortages in parts of the world, not even just with coronavirus and stuff going on. I mean, there's been people running out of food for a long time, and it's only getting worse. So the more land we plant with crops to make ethanol, that's less food that we're producing, and we're raising food prices and possibly worsening food shortages. Making this then uses fuel and electricity. It takes energy to harvest, to grow the corn, to harvest it, to then refine it into ethanol. Generally, we use gas or diesel in our farming equipment, and we have to use electricity to distill the ethanol and produce it. The bottom line is that when we're making ethanol from corn, we have what's called an energy efficiency of about 1.3. That means that we use 1 unit of energy to get 1.3 units of energy worth of ethanol. So it's like we burn a gallon to get 1.3 gallons, which is not actually that much of an overall benefit. Right? We're only gaining a little bit if you take into account all the energy that it takes to produce the ethanol. We're not actually gaining very much. Now, could we make this work somehow? Possibly. In Brazil, their cars run on ethanol. all gas bylaw is at least E20. The cars that are sold there now, the new cars, and a lot of the cars have been fixed up and changed, have had modified engines to allow them to run up to 100% ethanol, because Brazil grows a lot of sugarcane. And there they make ethanol from sugarcane. In that case, sugarcane-based ethanol has an energy efficiency of 8-1. So you use 1 gallon of fuel to produce 8 gallons of fuel when you're using sugarcane, because sugarcane is a much more productive crop than corn. And they've been doing this for decades. They've gotten really good at it. So with the right crops, yes, this can be made to work. Now, we can't grow sugarcane here. I think they grow it in Hawaii, maybe a little bit in Florida. Other than that, there's not much of the country that can grow sugarcane. However, it is theoretically possible to make ethanol from any plant matter. And there are experimental ways of making it from switchgrass, which is a native prairie grass. It grows, it grows wild around here. And theoretically, it has an energy efficiency of 20-1. That we would use 1 gallon of fuel to produce 20 gallons of fuel if we use switchgrass. Now, there's a lot of, development and innovation that has to be done in order to get it to that point. But theoretically, this could work. As you see in this picture here, that if we can really get this to work, you can travel 30,000 miles on 1 acre of switchgrass. That's a lot of fuel from 1 acre. But we need this new technology. All right, here's another one. In Who Killed the Electric Car, which now this was more than a month ago that we watched that in class, but a little blast from the past here. They talked about hydrogen-powered vehicles. These were a big thing 15 or 20 years ago. Don't hear so much about them now, and, well, we'll talk about why. Hydrogen is made from water, okay? You take water, you pass electricity through it, and it splits the H2O molecule into hydrogen gas and oxygen gas. You pass electric current, the bubbles come up, you catch them, you get hydrogen that way. So obviously we need energy to break that molecule apart. Then we have to store that. Now, hydrogen is a gas. And so in order to get it into a car, we need it under extremely high pressure. Or we can turn it into a liquid, but then that liquid has to be kept extremely cold, negative 423 degrees Fahrenheit. Okay? Then we could use it to power vehicles. We burn it, so it reacts with oxygen again. All that happens then is we're just running this reaction backwards. We're just taking hydrogen, we burn it with oxygen, we get water. And of course, we get some energy out. So the only emission given off is water vapor, just steam coming out the tailpipe. I mean, you could drink it if you cool it down. So that's pretty great. No emissions, right? No carbon dioxide. Well, here's the problem. It's that whole deal with the energy. We have to put energy in order to get it. The energy efficiency in this case is less than 1. It's even worse than corn-based ethanol. It takes more energy to make hydrogen than you get from using it. Okay? We have to use some other energy source to make the hydrogen, like fossil fuel, solar. Okay? We put a bunch of energy in to get less energy out than we had to begin with. So we're throwing energy away by turning it into hydrogen fuel. Now, hydrogen is very lightweight, which is good. So cars running on it, in theory, should be more efficient. They don't have as much weight in them. But it has low energy per unit volume. It's not very energy dense. So it's very light, but a gallon of hydrogen has a quarter of the energy that a gallon of gasoline does. So if you had a 15-gallon tank on your car, and using that 15 gallons of gas, you could go 400 miles. If you wanted to go 400 miles on a tank of hydrogen, you need a 60-gallon tank instead of a 15-gallon tank. And a lot of cars just don't have room for a 60-gallon tank unless you take out the back seat. So we need very large tanks, and they have to be kept under very high pressure. So hydrogen, could it be made to work? No, I don't think so, honestly. This is a fundamental problem, a fundamental law of physics. We cannot change the issue of energy efficiency, okay? It will always take more energy to make than we will get out of it. Now, maybe we can make it using some experimental solar panels, but why not just use those solar panels to make electricity? Speaking of solar, Could we use that to power cars? Well, we have these solar panels. You've all seen these. They're all over the place, right? More and more people these days have them just on their roof. It just sits there. There's no moving parts. It converts light energy directly into electricity. Now, people have them on the roofs of their houses, but you could put it on the roof of your car, right? Generate electricity, have it power a motor. Now, this is a basic rule of astronomy, there are about 1 or 2 kilowatts of solar energy per square meter. Okay, so think of how big a meter is. It's a little more than 3 feet. So, if you're sitting at a table right now, maybe your table's 1 or 2 square meters. Okay. The best solar panels today are about 25% efficient. So of that 1 or 2 kilowatts, they get about 25% of that. So let's be generous. Let's say 2 kilowatts, and they get 25% actually gets converted. So that's half a kilowatt per square meter. Think of how big a car is. Maybe there's a square meter on the roof, a square meter or 2 on the hood, okay? Or a couple square meters, maybe 3 square meters. What actually happens? Well, the car is too small. There's not enough surface area for solar panels. Here's an experimental car. It seats 1 person, and it is otherwise completely covered in solar panels. I don't know if you can tell, this thing is in the way, but it has like 3 itty-bitty little bike wheels. Okay? A typical size car completely covered in solar panels would generate about 5 horsepower. Okay? Which is not very much. Okay? Something like this can carry 1 person with a top speed of about 50 miles an hour. And of course, they can't run at night. They can't run on a cloudy or a rainy day. So if you lived in Arizona, where it's sunny every single day, and you only had to drive around in town and you never had to take anybody with you, and you only went places during the day, then maybe something like this would work for you. But for 99% of people, this is not a practical vehicle. Could we make it work? Not if we put them just on cars, not if we tried to have a car that was solar powered directly. But something like this could work. And in fact, it does work. You have a big solar panel, larger than the car, that sits there charging up a battery station all day long. And then a car comes along, plugs in, charges up the car's batteries from the batteries here in the charging station, and that takes maybe 15, 20 minutes. And then the car drives away. And then the solar panel sits there and charges and charges and charges for the rest of the day, ready for the next car. But on a car itself, there's just not enough power available in that area. Car companies have tried this. Toyota with the Prius, they experimented by putting panels on the roof of one of their Priuses, and it added about 4 miles to its total range. Okay. So that doesn't work. But they're useful for power plants. This technology keeps getting better and better. And theoretically, this could power the entire country if we really get the technology going and we really commit to building these plants. And these are great in situations away from the electrical grid, like a cabin or signs that just need to light up that you don't want to plug them in, charging stations like we have over here. Okay, anything like that away from the electrical grid, a solar power station is great. I was once with my brothers and my dad. We went on a fishing trip in Canada, and there was this cabin out in the middle of nowhere. It wasn't connected to the grid, didn't have an electrical generator, but it did have some solar panels up here. And the solar panels, like on the roof of the cabin, they sat there all day long charging up a whole bunch of car batteries so that then there would be enough power that you could have a couple light bulbs on at night. So you could cook and everything in the evening. Okay? That's the kind of situation that a small-scale solar station would be great for. Not so much for a car. All right? There you go. Now we know about some alternative energy sources that currently don't really work, but maybe. Have a good one.